Scope and excitement of physics. We can get some idea of the scope of physics by looking at its various subdisciplines. Basically, there are two domains of interest, macroscopic and microscopic. The macroscopic domain includes phenomena at the laboratory, terrestrial, and astronomical scales. The microscopic domain includes atomic, molecular, and nuclear phenomena. Classical physics deals mainly with macroscopic phenomena and includes subjects like mechanics, electrodynamics, optics, and thermodynamics. Mechanics, founded on Newton's law of motion and law of gravitation, is concerned with the motion or equilibrium of particles, rigid and deformable bodies, and general system of particles. The propulsion of a rocket by a jet of ejecting gases, propagation of water waves or sound waves in air, the equilibrium of bent rod under a load, etc., are problems of mechanics. Electrodynamics deals with electric and magnetic phenomena associated with charged and magnetic bodies. Its basic laws were given by Coulomb, Oersted, Ampere, and Faraday, and encapsulated by Maxwell in his famous set of equations. The motion of a current carrying conductor in a magnetic field, the response of a circuit to an AC voltage, that is signal, the working of an antenna, the propagation of radio waves in the ionosphere, etc., are problems of electrodynamics. Optics deals with the phenomena involving light, the working of telescopes and microscopes, colors exhibited by thin films, etc., are the topics in optics. Thermodynamics, in contrast to mechanics, does not deal with the motion of bodies as a whole. Rather, it deals with systems in macroscopic equilibrium and is concerned with changes in internal energy, temperature, entropy, etc. of the system through external work and transfer of heat, the efficiency of heat engines and refrigerators, the direction of physical or chemical process, etc., are problems of interest in thermodynamics. The microscopic domain of physics deals with the constitution and structure of matter at the minute scales of atoms and nuclei, and even lower scales of length, and their interaction with different probes such as electrons, photons, and other elementary particles. Classical physics is inadequate to handle this domain, and quantum theory is currently accepted as a proper framework for explaining microscopic phenomena. Overall, the edifice of physics is beautiful and imposing, and you will appreciate it more as you can pursue the subject. You can now see that the scope of physics is truly vast. It covers a tremendous range of magnitude of physical quantities like length, mass, time, energy, etc. At one end, it studies phenomena at very small scale of length, that is 10 power minus 14 meter or even less, involving electrons, protons, etc. At the other end, it deals with the astronomical phenomena at the scale of galaxies or even the entire universe, whose extent is of the order 10 power 26 meter. The two scales differ by the factor of 10 power 40 or even more. The range of time scales can be obtained by dividing the length scales by the speed of the light, 10 power minus 22 seconds to 10 power 18 seconds. The range of masses goes from, say, 10 power minus 30 kg, that is mass of an electron, to 10 power 55 kg, that is mass of known observable universe. Terrestrial phenomena lie somewhere in the middle of this range. Figure 1.1. Theory and experiment go hand in physics and help each other's progress. The alpha scattering experiments of Rutherford gave the nuclear model of the atom. Physics is exciting in many ways. To some people, the excitement comes from the elegance and universality of its basic theories, from the fact that a few basic concepts and laws can explain phenomena covering a large range of magnitude of physical quantities. To some others, the challenge in carrying out imaginative new experiments to unlock the secrets of nature, to verify or refute theories, is thrilling. Applied physics is equally demanding. Application and exploitation of physical laws to make useful devices is the most interesting and exciting part, and requires great ingenuity and persistence of effort. What lies behind the phenomenal progress of physics in the last few centuries? Great progress usually accompanies changes in our basic perceptions. First, it was realized that for scientific progress, only qualitative thinking though no doubt important, is not enough. Quantitative measurement is central to the growth of science, especially physics, because the laws of nature happen to be expressible in precise mathematical equations. The second most important insight was the basic laws of physics are universal. The same laws apply in widely different contexts. Lastly, the strategy of approximation turned out to be very successful. Most observed phenomena in daily life are rather complicated manifestations of the basic laws. Scientists recognized the importance of extracting the essential features of a phenomenon from its less significant aspects. It is not practical to take into account all the complexities of a phenomena in one go. A good strategy is to focus first on the essential features, discover the basic principles, and then introduce corrections to build a more refined theory of the phenomenon. For example, a stone and a feather dropped from the same height do not reach the ground at the same time. The reason is that essential aspects of the phenomenon, namely free fall under gravity, is complicated by the presence of air resistance. To get the law of free fall under gravity, it is better to create a situation wherein the air resistance is negligible. We can, for example, let the stone and the feather fall through a long evacuated tube. In that case, the two objects will fall almost at the same rate, giving the basic law that acceleration due to gravity is independent of the mass of the object. With the basic laws thus found, we can go back to the feather, introduce corrections due to the air resistance, modify the existing theory, and try to build a more realistic theory of objects falling to the earth under gravity.